and welcome to Diksha Vedantu CBSE English. I'm your Aditi Ma'am, and today we are going to dive into a very important chapter, work, energy and simple machines. That is a new topic added by CBSE and NCERT. Now, beta, we all know this chapter has a lot of importance. I would rather say in physics overall. And if you are planning to take JEE, NEET or science in a PU1, PU2, +1, +2, then this chapter is really important. And to make this chapter a little bit fun, I have included fun facts, lots of questions, lots of theory and lots of numerical as well. So you get everything, a power package in this single video. You don't have to go anywhere. Your PT tests, your half yearly, your pre-boards, boards are done in this single video. That's it. I can guarantee that. So, beta, let's start with work, energy and simple machines with full power. Even though the power word is missing from our topic as of this session, we will do that. Okay, we will bring full power. Okay, now beta, let's start with a rather fun fact. Okay, what's the first fun fact? Oh, what's the first fun fact? Okay, you know, one burning matchstick releases about 1000 joules of energy. 1000 joules of energy. What is joules? We'll learn in a second. Enough work to lift a 1 kg of book to the top of 100 meters building. So that one simple matchstick is producing so much energy that it can actually carry a book, a 1 kg book to the 1000-meter building. Are these same, ma'am? Let's try that. Let's burn the matchstick and a book will climb a 100-meter building. Is that the case? That's actually not the case. And that is what we have to learn in this video, beta. Science has its own language. And that language does not necessarily mean our generic English language, as you will be seeing in this particular fun fact, right? So beta, that's a tone set for this session, that this chapter is going to be a rather interesting with the help of scientific language. Okay, now what will we be studying in this particular chapter? First, work done. What is work? Okay, work, energy and simple machines. So the question starts with, ma'am, what is work? So that's exactly what we are going to see. Then we are going to move to zero work, negative work, positive work, work energy theorem, a very important thing that we have in this particular chapter, our work energy theorem, forms of energy, and we all know a little bit about that, but we will dive a little deeper on that. That is kinetic energy, potential energy, conservation, power. We have the chapter, we have the topic in our chapter, but it's just missing from the title. That's it. Then the new chapter, the new topics we have are simple machines, which include pulley, inclined plane and lever, and very important numericals on these. Okay, then we have a few numericals and questions as well. Okay, beta, let's start with the very first thing, that is beta your work. Now ma'am, in science, okay, in science, work has a very precise meaning. What is that meaning, beta? Work is when I say I did lots of work. I did 4 hours of work today. I did 5 hours of work today. What do we mean by that? We mean that I studied for 5 hours. Your father means that he went to his job and he did 9 hours of job, 9 hours of work today. For your mother, it means something else. But what in physics language does work means? Work means, beta, in simple language, let's understand that work means whenever a force is applied. We studied force in the last chapter, right? Whenever a force is applied, okay, you have this box, okay, you have this small box. Can I apply a push or a pull on that? That is our force, right? That we studied in the last chapter. So let's say a force of F is applied on this block. So whenever a force is applied and that force produces some, that force, beta, it produces some, why is this not happening? Yeah, that force, it produces some displacement for this block. Now the block that was here at this position, it has moved with the displacement of S to a position of this point. Now let's say this point is A and this point is B, beta. So what happens? The block was here, I pushed it, I applied some force on it and it got displaced from its position. What are the other examples? Ma'am, when we fight, I push my brother or sister, and he displaces, okay, or I displaces, right? When I push an accelerator, my car moves, my truck moves. Whenever the driver pushes the train lever, the train goes ahead. All are examples of what? We are applying some force, we are getting some displacement. So work beta is simply force into displacement. Force into displacement. So work is what? Work is beta force into displacement. Now this displacement we have taken as S. Now if you are in 9th class, that's the only thing you probably right now have to study. But here is a very important thing that we missed here in the definition. That is beta force applied, and it gives some displacement, but in the direction of displacement, that means, what am I trying to say? I'm trying to say beta that you have this box, okay, you have this box and you're applying a force in right hand side, horizontally right hand side, and your box is actually also moving with the displacement of S towards the right hand side only, and that's the basic formula, basic definition of work, that it means force into displacement, force applied, and due to that displacement happened, but that force is applied in the direction of displacement. That force is applied in the direction of displacement. Now to understand it better, understand this one particular thing. Now it's a little high level, okay, it's a little bit of high level concept, but if you understand this, you will be very good with your concepts, okay. Now beta, you also carry your trolleys, okay, when we go to stations, bus stands, airports, we all have our bags, right? So what do? We pull them like this at this particular angle. I'm not pulling it horizontally, right? I have a bag, I tilt it, and I pull it towards me like this. It is slanted, okay. This is me, okay, me, and we have this bag and it is coming behind us, it has wheels, so it is tilted, and my force is like this. My force is, I'm pulling it, right? I'm pulling it. So let me draw this at here. Let's say this is the bag and this is the force I am pulling this bag with. This is the force I am pulling this bag with, and it is getting displaced. Okay. So after some time the bag reached here. After some time beta, the bag reached here. Okay. Now what is happening? I am applying force in the slanted direction. I am applying force in a slightly upward direction, in a slanted direction, but my suitcase, it is moving horizontally. It is moving in this direction. So this is horizontal, but my force is not horizontal. And what did I wrote? I wrote that force applied in the direction of displacement. So is this force applied in the direction of displacement? No ma'am, that is not the case. Then how will we write? What is the work done here? How will we write that? Very basic simple formula. See, right now we don't have some very good mathematic tools with us, like vectors, like components, like resolution, like trigonometry, that you might have heard, but we'll soon have those in class 11th. In class 10th you will study that. In class 11th you will incorporate that in physics. Now beta, what happens? See, now this force is slanted, right? It is slanted, but my bag is moving horizontal, right? So can I say that this force is applying some horizontal component that is moving this bag horizontally? This force is applying, it has some horizontal component to it. It is pulling my bag in the horizontal direction as well. So can I write let F, and it is in the direction of displacement. It is in the direction of displacement. So I will write F. It is in the direction of displacement. Can I write Fs? Okay, and it has some vertical component as well, Fv, let's say, but that is of no use right now. Okay, that is of no use of us right now, so let's just ignore it. Now beta, what will I write the work done here? What will I write the work done here? Will I write F into S? or will I write Fs into S? What do you think? You tell me in the comment section with the timestamp. Tell me what will you write the work done for this particular case. Ma'am, it's force into displacement, but force in the direction of displacement into displacement. So which force is in the direction of displacement? Ma'am, Fs, right? So actually beta, the work done will be Fs into displacement. Understood? Understood? See, you are working on you're pulling something, you're pushing something. When you're pulling something, you want it to come near you, right? So that you can say, I did some work. When you're pushing, it should be going away. So you can say that I did some work, right? So that is what work is. Work is beta, force applied in the direction of displacement multiplied by displacement. And due to that force, a displacement happens, and that is what work done is, right? Now, just like I resolved, we call it F. I resolved F into its component along the direction of displacement. Hearing what I'm saying, I resolved this force into its component which is in the direction of displacement, and that the multiplication of these two will give me the work done. Can I resolve this displacement? This is the displacement. Can I resolve this displacement in the direction of force? Will that be a work done? Only work done, only condition is this work done, this force should be in the direction of displacement. Now, force comes in the direction of displacement or displacement comes in the direction of force. Both are same. They should be in the same direction. That is the only condition, right? So, what will I do? This is my force, applied force. I will resolve this S, this displacement in the direction of force. So, this is beta SF. Displacement in the direction of force. So what will be the work done here? Ma'am, work done will be again F. Now this is F, but displacement this time is S into SF. That is displacement in the direction of force. Understood? Something understood? Something goes into your brain. Now, why I'm saying all this? Because beta, the definition includes work done is the force is the or you can say sorry, work done is the force applied on an object. It produces a displacement, and that force should be in the direction of displacement. Done? Understood? Now beta, again a very important thing that also is that this your force beta, this should always be constant. This should always be constant. That means if I applied, we know the SI unit of force is Newton. So if I applied 20 Newton of force at this point, at point A, and when this box reaches point B, the force is still 20 Newton. It is still 20 Newton. That is the case. So force will remain constant throughout when we are calculating the work done. Okay, so that is the meaning of work done in scientific language. Then this is the main formula you have to remember. Now beta, this is the ideal case that force is horizontal, displacement is horizontal. That's how we have to study. All these cases will come in higher classes, but you get an idea why we call it that force in the direction of displacement into displacement is the actual work done. Done? Okay, let's move on to the next point we have beta is your SI unit of work. Now we studied the SI unit of force was what? It was Newton G. Okay. Now beta, the SI unit of work, it is what? It is called joule. Some people call it joule. Okay, that's on you, whatever you want to say. But the SI unit of work is beta, it is joule. It is joule. Now what you have to see is this, that we calculated that work done is simply force in the direction of displacement into displacement, right? Now beta, what was the SI unit of force, that was ma'am Newton. And what is the SI unit of displacement? Simply meter. So beta, work done equals to Newton meter. That is also the SI unit of work, which is equal to joule, which is equal to joule. Now also, do you know one more thing? This is very important, okay? Do you know one more thing? F is equal to what? M into A. Right? So can I write here that work done is also beta force into displacement, but this force is M into A into displacement, right? What is the SI unit of mass? Ma'am, simply kg. What is the SI unit of acceleration? Ma'am, meter per second square. And what is the SI unit of displacement? Ma'am, simply meter. So this kg meter square per second square, or you can write it as kg meter square s minus 2. This also will be beta your SI, your units of force. What is the SI unit? SI unit is joule. SI unit is joule. Now joule, this 1 joule is equal to 1 Newton meter, or I'll tell you about Newton meter 1. But this joule is also equal to Newton meter, which is also equal to kg meter square per second square. Understood? So that is the whole criteria. 1 joule equals to 1 Newton plus 1 meter. That means 1 joule of work is done. 1 joule of work is done when 1 Newton of force is applied on the direction, in the direction of displacement, and the displacement is 1 meter due to this 1 joule of force. Understood? How to write it? 1 joule of work is done when a force of 1 Newton displaces an object by 1 meter in the direction of force. This line is very important, in the direction of the force. So this object is applied with the force of 1 Newton, and it got displaced by a displacement of 1 meter in the direction of force. This is 1 meter in the direction of force. Understand? Great. Okay. Now beta, this is some knowledge about scientists. Now let's see this graph. This is very careful. Now what we are talking about beta here is, we are talking about that force is always constant. Force right now till class 9th, we are talking about that force is always constant. Let's say my force is 10 Newton. So it is always 10 Newton. Can you see it? It is always 10 Newton, right? But the box is getting displaced, right? The box was here, but now the box reached at a second point, that is here. So it got displaced. Let's say it got displaced by 1 meter. This is 0 and this point is beta 1 meter. Okay, so by a constant force of 10 Newton, the object is displaced by 1 meter. Right? Now, you tell me one thing. This is force, right? This is displacement. What is the area of this whole thing? This, what do you call, length, and this breadth. What will be the area? Ma'am, this is simply a rectangle or a square. Let's take it length into breadth. Area will be simply length into breadth. Length is what? It is displacement. Can I write displacement as S? Right? And breadth is what? This is the force. This is the force, right? So this will be simply F into S. This is the area. This is the area, and area equals to F into S. What is also F into S? That we just studied. Ma'am, we just studied that work. That work is also F into S. That means beta, work, our work is equal to area under Fs graph. Fs graph. Done. For constant force. That is the one very important thing you have to write. For constant force. Done? Understood? This is the main thing we are studying here. Okay, done. So what gives, if you are given a graph, how will you find the work? We will find the work of an fs graph when f is constant by multiplying, by finding the area under that graph. Done? Understood? Pretty easy, and I hope it's a bit interesting as well. Something different from the normal science we are studying till now. Right? So this is the whole concept of work. It's SI unit, the graph, and some of the very main important point. First is that force is in the direction of displacement. In the direction of displacement. Very, very, very important point. Done? Then beta, the second important point is, it was what? Force is constant. Force is constant right now till your class 9th. Done? Understood? Okay, let's move on to the next topic, that is beta. When we are talking about work, we have to talk about the kinds of, or the types of, let's not call it types, but the kinds of work. When is work positive? When is work negative? When is work zero? Ma'am, can the work be zero? Yes, when you scroll reels and just sitting there doing nothing, well, in that time work is zero, right? Well, maybe physically it is, scientifically maybe not, maybe it is. Let's find out. Now beta, I want you to get up. I want you to get up and you start pushing any wall. Start pushing some wall. So you're applying some force. Of course, you're applying some force, right? But is it moving? Is it moving? Is the wall moving? Now, if you are not Great Khali or rock, the wall will not move. Definitely. And definitely not our Indian cemented walls. So, beta, look at this carefully. The work is basically force into displacement, right? Now, if work has to be zero, that is F into S, right? That is the work. If work has to be zero, if it is zero, that means 0 is equal to F into S. Now, this term will become zero only when what? Only when either F is 0, either F equals to 0 or S will be equals to 0. If I multiply 2 with 0, it will be 0. If I multiply 0 with 2, it will be 0, right? So, if F is 0, S is something, but F is 0, my work is 0. If I am applying force, but the wall is not moving, so displacement is 0, but I am applying force. So, force has some value, let's say 200 Newton, but displacement of the wall, that is 0. So, work done is what? Work done is 0. So, beta, for the displacement of wall, see, it's either F equals to 0 or S equals to 0. Push a rigid wall as hard as you like, no displacement, so no work. You feel tired because the pizza you have eaten has given you some kind of energy, but not a lot of energy to move the wall. Okay? You feel tired because the pizza, the mitochondria has formed some energy, right? In your whole body, you are applying force. So, you are applying energy, your internal energy, right? So, that's why you feel tired. But in physics, work has not been done. Done? Okay. Now, beta, this is a rather very, very great example. But if it would have been better if we had trigonometry to explain this. But right now we don't. So, let's just understand this in basic science. Okay. So, a girl is carrying a box. Okay. I am carrying a box. Let's say, okay, I am carrying this glass, okay, this mug, and now I am moving. You tell me one thing. Am I applying any force on this particular mug? Of course I am. Why? Ma'am, you are not moving it, you are not pushing it upwards or downwards. But if I leave it here, I'm so scared to leave it. If I leave it here, it will go down, right? It will go down. Under what? Under gravity. So there is some force on this in the downward direction, due to gravity. Okay, gravity pulls everything down. But I am applying a force upward. We studied in for how forces affect motion, right? So a force upward is also applied by me to balance this mug so that it does not fall downwards, right? Now I'm moving anywhere, does not matter. My force is applied upwards, right? And I am moving and the displacement is in this direction. I was here, let's say I am here, and now I moved here. Okay, so this is the displacement that is in horizontal direction, and the force is what? Force is in the upward direction. Force is in the upward direction. So these are perpendicular. Okay, perpendicular. And in case of perpendicular, whenever the angle between a force and a displacement is 90 degrees, we say that the work is not done, or we say that the work is zero. You will understand later in higher classes, but for now just remember, whenever the work force is in the upward direction, the displacement is in the horizontal direction. So I'm moving like this, okay? But in this direction, the angle between force and displacement, is 90 degree. And when the angle is 90 degree or they are perpendicular, the work will be zero. Okay? Her force is up. When a girl is carrying a box, walks forward. Okay? Her force is upward. Motion is forward. That is perpendicular between force and displacement. So that means zero work by that force. See, I am applying this force in the upward direction, direct upward direction. Because of this force, this mug is not moving. This mug is moving because I am moving, right? But the force is in the upward direction. But this upward force is not making this mug move, right? So the work done by this upward force is not making this mug move, and hence the work done is zero. Done? Understood? Okay. Now beta, let's move on to the next, that is positive work or negative work. Now beta, I told you when I gave you the definition of work that this force should always be in the direction of displacement. Should always be in the direction of displacement. But let's rectify a little bit. Okay, when the force is in the direction of displacement beta, that's actually your positive work. When the force is in the direction of displacement, what example we have? We have you pushing a wheelchair forward, you do the positive work on it. You have an NCERT image on that, right? So there is a wheelchair, you're pushing it forward. So your force is in that direction and the displacement is also in that direction because wheelchair is moving ahead, right? So this is how you are moving. Force and displacement are in same direction. They are in same direction. That means the work beta is positive. Okay, next beta, negative work. Now I say that you applied force in this direction but displacement happened in this direction. Ma'am, how can you say that? How can you say that if I apply a force here, the displacement will be in the opposite direction? This is force, this is displacement. Can this happen? Now in general cases it can't, but you tell me for different forces. Okay, this is a car. This is a car moving on a road. So displacement in that direction, right? Displacement is in that direction. But we studied about frictional force in the last chapter. Where is frictional force happening? In the direction opposite to the direction of motion, right? So this is the road. So friction force in the opposite direction. Frictional force is in the opposite direction. Understood? And that is why beta, this frictional force is not in the direction of displacement in this case. This frictional force is not in the direction of displacement in this case. And will that be a negative work or a positive work? Ma'am, applying force, friction. Imagine, see, from the friction point of view, friction is trying to stop this car. It is applying force in the opposite direction, but it is still moving in the opposite direction. So from the friction point of view, the work done by frictional force, how will we write it? Work done by frictional force is it is negative. Why beta? Because the direction of force and displacement is opposite. They are moving in, or they are being applied in opposite direction. Understood? Understood the main point here we are talking about? They are being applied in the opposite directions. Okay? Oh, I accidentally closed it. Turned it off. Yeah, it's getting really hot here. Done. So work done by a frictional force applied on a moving car which is moving in the opposite direction of the frictional force is negative. Done. Now one more example was there in your book, that a girl, you are playing football and a goalie, it tried to stop that ball. So what is happening? Let's understand it from a cricket perspective or a football perspective, whatever. Now when the goalie stops the ball, or when MS Dhoni catches the ball in the when he is keeping, right? So when he catches the ball, he goes a little behind, but the ball is stopping. Ball is moving this side, but he is applying force on that direction. Ball is coming from that direction, he is applying force on that direction. So in that case, work is what? Work on that ball is negative. When the goalie, when she is trying to stop the football, she is trying to stop the football and she is applying the force in that direction, but she'll go a little behind, right? Due to the force, due to the velocity with which the ball is coming, she will go a little behind. Her hands will go a little behind and she will apply a force on the opposite direction, and hence the work will be negative. Understood? Everybody, if you have any doubt, let me know in the comment section, and if you like the session, press the like button, and do let me know in the comment section as well. It gives us very much motivation. I swear, reading those comments that ma'am, thank you so much, ma'am, you're like an angel, it makes my day. Okay, so do let me know in the comment section if you liked it, if you don't like it, anything. Okay, very good. Now beta, let's move on to another topic, a very important one, that is your energy. Now beta, work, energy and simple machines is our topic, right? Work is mostly done. It was the basics of this chapter. Okay, but what makes this chapter really interesting is how we connect this work with the energy. Now what is energy? Ma'am, I have so much energy today. Do you have more energy to run than your younger brother who's like 5 years old? Of course, right? So your capacity to run is more than your younger brother. That can I say, your capacity to run is more, and running is what? Doing the work. So your capacity to do the work is more. That means you are more energetic than your younger brother. And that means energy is what? The capacity to do the work. Nice example. Understood? So beta, the capacity to work, the capacity to do the work, or an object having the capacity to do the work possesses energy, or that is called energy. Okay? I ate a very healthy food and now I have lots of energy. I have lots of energy to run. I have energy to run, and that is what? I have the capacity to do the work, right? There is energy inside me that gives me the capacity to do the work. Understood? That's the whole thing. Now beta, okay, a thrown cricket ball can knock the wickets, a raised flower pot can dent the ground. Okay, so what is happening? There are again examples of these things in your NCERT. So what is happening? Like there is Virat Kohli. You know, the shot of Virat Kohli is so accurate. The MS Dhoni is so accurate. So what is happening? They throw the ball. Throw the ball and they give it some energy. This is a ball, okay, and it is going, it is traveling. Why it is traveling? Because beta, the player standing beside, he used his hands, he ate very healthy food. Virat Kohli eats very healthy food, so he has lots of energy. He gave that energy, he gave his energy to the ball. What did he do? He gave his muscles energy to the ball. Okay, so he transferred his energy into the ball. Now, if Virat Kohli throws the ball, he has more capacity to throw the ball than, of course, I do, right? Now, beta, so his capacity of throwing the ball or doing the work is more than me, right? That is one thing. Now, beta, when this player throws the ball, and here we have some wickets, right? Here we have some wickets, and this ball will come and it will knock these wickets out. It will knock these wickets out and they will fall on the ground. Now, what is exactly happening? this player is transferring his energy into the ball, then ball is traveling with that energy. Now ball has the energy of Virat Kohli in itself. The ball has the energy of Virat Kohli in itself, and then it goes and it hit the stumps and these wickets fall down. So it does some work. Okay, eventually we knock the ball out and we say Virat Kohli knocked the stumps out, but actually ball knocked the stumps out, right? But how did the ball knock the stumps out? With the help of energy that it got from Virat Kohli, right? So that is the one thing. You understand how this is happening? So beta, this is the work of energy. It is providing the ball a capacity to knock these wickets out, a capacity to do the work. Done? There is one more example, that we have this ceiling, we have this very beautiful home, okay, and here above the home we have some flowers, okay, we have some flowers, and again in the Virat Kohli, it is the time of, let's go into the past, and Virat Kohli is playing in the streets, so he again gave some energy to the ball, right, and it hit this pot and this fell down. Okay, this fell down. I'm not that good at drawing, but okay. Now this pot fell down on the ground. Now beta, what happens? This pot will break down. Obviously, in general case, this pot will break down into pieces. Why that happened? Because beta, this pot also had some energy in it. Ma'am, it was just resting. Yes, that's the whole point. Where it was resting is the another point. It was resting at a height of h. At a height h. Okay, so it is above the ground. Above the ground. If I keep it here, it will come down, right? So it has some energy in it. Gravity will pull it down. It has some energy in it. It has some capacity of energy in it. And when it is allowed, it did the work of coming down. Right? That's the analogy you have to work and think through. Okay? Both gained energy from work done on them. There, in this ball, the work was done on this ball with the help of Virat Kohli's muscles, and it broke the stumps. Right? In here also, this ball gave its energy to pot and it fell down because it already had some energy in it. The work is done on this pot by this ball and it came down. It fell down. Right? That's the whole process of energy. Then, now beta, what is a work energy theorem? That says that when you give some energy, when the energy is changed, there is a change in energy, work will happen. That means you are driving a car. You are driving a car and it has a big engine in it, right? It has a big engine in it, obviously. Now, this engine gives the power to its wheels and then it travels some distance. Right? So work is happening. Work is happening. Why work is happening? This force is applying some force. When you push an escalator, a force is being applied by you, right? So there is a force, and it got displaced. So work is done by this car. But how this car is working? This car is working with the help of fuel that we put in this engine, or when we pressed the accelerator, but mainly the energy that is being generated by this car. So beta, and of course, when we move around in our car, we use the fuel, right? We use the energy. So first fuel was very high, energy was good. As soon the fuel is trying to end, it is going to end, and you will see when very low fuel is ending, your car is like going to stop, right? Duk, 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 duk. Okay, so it stops. So what is happening? Change in energy is happening, right? Change in energy is happening, and because of that beta, displacement or work is being done, and that is our work energy theorem. That is our work energy theorem. That means a change in your energy will do the work. Okay, that is what work done on an object is equal to the change in its energy. The work that was done by Virat Kohli on this ball led to the change in energy of this ball. It was at rest, it didn't have any energy. Virat Kohli gave this ball its energy. So basically, he worked on this ball. He threw this ball. So he did some work on this ball, and because of that work, this ball changed its energy from 0 to a lots of energy. We will talk about the specifications, right? So Virat Kohli did some work on the ball and changed the energy of that ball. Understood? Clear? Basic? Right? Very good. Now beta, let's move ahead with a very specific example. Okay, we have a very important thing that this theorem works even for systems of objects and non-constant forces. Like beta, here we are talking about just constant forces. So, but this work energy theorem, when we talk about theorem, it applies to a lot of places, not just one particular scenario. So it works for non-constant forces as well. It makes tough problems very easy, and you will see in some time because we are going to do the problems. Okay, now beta, there are several different forms of energy, and the very first form of energy, and we are going to focus a lot of our time on this particular form, that is our mechanical energy. That is your mechanical energy. Mechanical energy means the work done by your engine, the work done by some machine, the work done when a motion is happening, when a position is changing. So all those things we talked about, when you remember, we talked about this pot. So why does this has energy? Because of its position. I told you, right? It is on a height h. So because of its height, it has some energy in it, and that beta is your mechanical energy. Okay, we have thermal energy, right? We give heat, and whenever a pot falls, you'll see that if you touch that broken pieces of the pot, you'll feel they're a little hot, won't you? You'll see they'll feel a little hot. So the energy is converted into thermal energy. What is conversion? Just a second, we'll learn everything about it. Then beta, we have light energy. We'll study in the next class the light chapter, and we know light is an energy which enables us to see this beautiful world around us, right? Next beta, we have electrical energy due to the motion of charges. You must have studied by now that we have positive charge, we have negative charge, right? Now, the capacity to do work is the actual definition of energy, right? So, if basically what will they do? They will attract towards each other, but I'm holding them. I won't let you go towards each other. I'm that cruel someone who won't let you guys meet, okay, with your friends. So I am holding these two people apart. One is positive, one is negative, but they are getting attracted, they want to go sit together, right? But I am holding them again. So they have some capacity in them, they have this urge in them to, whenever I leave them, the capacity, they will attract towards each other, and they will come together or sit together, whatever you want to say. Okay, so they are building a capacity in them that whenever I'm holding them, they have the capacity to do the work, and when I leave them, they actually do the work and go and be together. Okay, then beta, we have sound energy. So of course, when a pot falls down, the neighbor auntie comes. Why she comes? Because he heard the sound, so that energy got converted into sound energy as well, right? Then we have nuclear energy. We talked about in the atom chapter, journey inside the atom, we talked about at the center of the nucleus, at the center of atom we have nucleus, and we have so many positive charges in them, protons, right? So that the forces between protons and neutrons are called what? Nuclear forces. Because of that, we have nuclear energy that we use all around us, right? Then beta, we have chemical energy. The pizza you ate still gave you some energy. Okay, still gave you some energy. So that is your chemical energy in foods and fuels. When we drive a car, a fuel, our petrol, our diesel, all those are what? These are chemical energies. Then we have beta convertible energy. Convertible is what? Beta, you must have heard this somewhere, that energy can neither be created nor be destroyed, but it can be changed from one form to the another. That is the main motto of energy when we talk about, right? That is called conservation of energy. And how conservation of energy happens? Because of the conversion of one form of energy into the another. Pot has some energy in it, but when it falls down, there is some thermal energy, there is some sound energy, there is some other kind of energies that it releases. So basically it had some energy, all that energy got converted into sound energy, thermal energy. Okay, so that comes under the conservation of energy, and that is our next topic. But before that, we want to study this form of energy, mechanical form of energy. It is very important, and beta, it has two types. One beta is your, now mechanical. We talk about mechanical when things are in motion or when they are in rest because of their position, right? Just a second. Let me have some energy from this chai. Okay. Now beta, mechanical energy is converted into two types. We talked about motion, we talked about position. So on the basis of motion, beta, the energy, the objects which are in motion will have some energy, and that will be your kinetic energy. Kinetic energy. And what is the name of the energy because of the position? I know you know all it, so let me know in the comment section fast. Okay, so the second form of energy on the basis of position, but more like, if we go more into specifics, I will call it height. More on the basis of height, right? That is beta your what? That is your potential energy. We will study these one by one, and from this potential energy you can relate the pot example I gave you. Done? Okay, let's quickly see through it. Now beta, first is your kinetic energy. Okay, before with that, we have a fun fact number 2. What is the fun fact? Ma'am, eating just one apple gives you roughly 200,000. Now you know what 1000 joule is, right? This is what you write J. This is your J. What is J? SI unit of work. And what is that? That is joule. This is joule, right? So beta, one apple gives you an energy of 200,000 joule of energy, chemical energy, and that's enough to power a phone charger for several minutes. So ma'am, can we just let our phone eat the apple? That is where the conversion comes from. Okay, you need electrical energy for phone, but this is chemical energy. That's the whole point. We can get energy from apple, but unfortunately our phones at this moment in 2026, they can't. Okay, maybe in 2030 you make a gadget which eats apple and works for several hours. Okay. To the new gadget that eats apple, let's study our next topic, that is kinetic energy. Now, what is kinetic energy? Beta, we talked about the objects which are in motion are called, they have kinetic energy. The objects which are in motion, they possess an energy, and that energy is called beta kinetic energy. Understood? Now, this object possess, this object has this energy due to what? Due to its motion. Okay, so rolling of ball, when you're traveling in a car, when you're moving on a bicycle, all these things, all these objects have an energy that is called kinetic energy. Done? They have a kinetic energy in them due to their motion. Okay. Now beta, okay, this statement is very good. We will learn that. Before that, we want to see what is the formula for kinetic energy. Okay. Now for kinetic energy beta, we have a very specific thing. Now work is what? Work is simply beta. Now energy is what? It's simply the capacity of doing work. Simply the capacity to do the work. And what did we study in work energy theorem? What did we study in work energy theorem? Ma'am, we studied that the work done is equal to the work done is equal to the change in energy. It is equal to the change in energy. Keep in mind, we'll come back to it. Okay, so basically beta, work done mathematically work is equal to energy. Why do I say this? Mathematically beta, work is similar to energy. Okay, how will I tell this? But the formulas are different, but their units are same. Their units, both of their units are joule. Okay, work also is given by 100 joule work, 100 joule energy. But how do we differ? This is the work done. This is the capacity to do the work. Okay, that's the difference. Now beta, my work is what? Force into displacement. That is my simple definition of work. Okay, now beta, how can I write this in the form? I want a formula for kinetic energy. Now an object is moving. So this work done will be what? This is change in energy, but due to its motion, the energy is what? Kinetic energy. So can I write change in kinetic energy? Change in kinetic energy is equal to force into displacement. Okay, that's the main thing beta. Okay, now look at this very carefully. Oh, this is what the slide. Okay, I got the definition for you as well, but okay, great. Now beta, what you have to do, see, this is the main part here. Now let's move on to work done is what? Force into displacement. Can I write force as m into a? Can I write force as m into a? Of course ma'am, you can write force as m into a. Now remember the third motion of equation, third equation of motion, and that was what? V square equals to u square plus 2as. Now I want displacement, right? So displacement will be what beta? V square minus u square divided by 2 into a. Is this clear? Is this clear? Till here everything is clear. Now can I put this value of s in here? This is also s. This is also displacement. This is also displacement. So can I put here v square minus u square divided by 2 into a. Is this clear? Is this clear? Now beta, this a and this a gets cancelled. Acceleration, and what is left? M v square minus u square divided by 2, right? And this is your work done, or you can write this is the kinetic energy, or change in kinetic energy, right? Now beta, can I write the final minus initial? Can I write change in kinetic energy? Can I write, see, change in kinetic energy? Can I write kinetic energy final minus kinetic energy initial? This is clear. Final position minus initial position, that is change in, that is displacement. Okay, change in position, right? Per unit time, yes, but change in position. Displacement is simply change in position, right? Simply we have change in kinetic energy. So look at this here. If I say that originally, what is this meaning? My object is in motion. Okay, see here, my object, this car, this is in motion and it is moving with velocity v. Initially it was moving with velocity u when I started the time, when I started to record. What if when I started to record the initial velocity was 0 or my object was at rest? That means u is 0 and v is simply v. That is my final velocity. U is my initial velocity. When I started the time, the object started from rest. We studied all this in the describing motion around us chapter, right? Let's go back. U is now 0. So u is now 0. So can I write m v square minus 0 square divided by 2? And this is change in kinetic energy. Kinetic energy final minus kinetic energy initial, or instead of doing this you simply write kinetic energy. Okay, for now let's just write kinetic energy. We'll understand this later, don't worry. Okay, so beta, can I simply just rearrange this and write it down as half this 2 m v square? Is that true? And that beta is the final expression of kinetic energy, and I cannot stress how important this is to your higher level of studies as well. This energy topic is very important, but this formula of kinetic energy, it will be on your fingertips. If you study science, if you study physics, it will be on your fingertips. Anybody will wake you up at 3 a.m. and like, what's the formula of kinetic energy? You're like, half mv square. And you'll go back to sleep. That's how common and important this formula is. Okay? Okay. So that was all about kinetic energy. Now beta, one more thing. Of course, m is what? Mass, and v is your velocity, and this is the main formula, half mv square. Now let's see a little bit of mathematics in it. What we said kinetic energy is half mv square. Right? Now, there is a sentence written here, doubling the velocity makes kinetic energy 4 times bigger. Okay, let's see what this means. This means that initially, okay, again, my car is moving. Okay, now I have an initial velocity, or let's say, first it was moving with v. After some time, it is moving with velocity. The velocity gets doubled. So, it is moving with 2v. Now, it is moving with 2v. So this is your final velocity, and this was your beta initial velocity. V, you will write it as u. This is your initial velocity. So here kinetic energy is the final one. Here the kinetic energy is the initial one. Right? Now they asking us how much kinetic energy will increase if the v is doubled. Okay, so let me find out the initial kinetic energy. Initial kinetic energy beta will be simply half m u square, and this u is what? Simply v. So this will be half m v square. Right? Then this is the final kinetic energy. What will be the final kinetic energy? Final kinetic energy will be half m v square. Right? V square is what? 2v. Final energy is what? Final velocity is what? 2v, half m 2v square. Done. So beta, this will be half m 4v square. Now one thing you don't have to do is to cut this. It's to cut this 4 with 2. That's the one thing you can't do. Okay, what you have to do is just take this 4 in front. What am I saying? Just take this 4 in front, and we have 4 in front, okay, and half mv square. Can I write it down as 4 I took in front, half mv square, everything is same. What is this half mv square? Well, this is initial kinetic energy. So kinetic energy final, kinetic energy final is equal to what? It is equal to 4 times, this is what? Initial kinetic energy. Kinetic energy initial. That means beta, kinetic energy final is equal to 4 times kinetic energy initial, only because of what? Only when we changed the velocity, we doubled the velocity. We doubled the velocity. First it was v, now it is 2v. Understood? That kind of question can also come in the examination. They'll ask you what will be the ratio of initial and final kinetic energy if the velocity is doubled or tripled. So for ratio, what will you do? You'll just divide final kinetic energy to the initial kinetic energy, right? Final kinetic energy is what? 4 into initial kinetic energy. Initial kinetic energy is initial kinetic energy. This cancels out. So the ratio of final kinetic energy with initial kinetic energy, it comes out to be simply 4:1. Understood? So if it is 9, 3 times, 3 square is 9, 9:1. So basically kinetic energy is directly proportional to the square of velocity. Understood? It is directly proportional to the square of velocity. Also it is directly proportional to the mass of the object. So these are the two things that you can remember. It will be a very beneficial thing for you. Done? Okay, now moving on to the next thing, beta, we have a question for you. Great. If the velocity of a vehicle doubles in magnitude, what will be its kinetic energy compared to the original value? We just did that even before the question came. So again, you write it down in your homework and you write it down in your notebook as well. Done? Okay, next question. In one of their fastest deliveries, an Indian cricket bowled a cricket ball with approximate mass of 0.2 kg. So what is given? What is the one sole motto of Aditi Ma'am's class? We write as we read the numerical. Okay, so mass of 0.2 kg of ball is given and it is traveling at a velocity of 154.8 km per hour. 154.8 km per hour. Calculate the kinetic energy of the ball at the time of its delivery. Now beta, what is the formula of kinetic energy? Ma'am, very simple. What is we have to find? We have to find the kinetic energy. Okay, we have to find kinetic energy. And what is the solution? Ma'am, solution is simply the formula of kinetic energy. Kinetic energy is half mv square. Now one thing you have to take care of, all the units should be in SI units. All the units should be equal, right? So kg is an SI unit, but kilometer per hour is not an SI unit. Meter per second is an SI unit. So what will you do? To convert kilometer per hour into meter per second, what do? We multiply by 5/18. Right? We multiply by 5/18. So this will be your meters per second. Now I hope you do the calculation because I have told you so many tricks to do the calculation. So make sure you try yourself and give the answer in the comment section. The slide number is 29. The slide number is 29. Give the calculation, answer of calculation in the comment section. All of you have to. Okay, I'll just fill the this will be half m. M is what? 0.2 kg. Done? Into 154.8 into 5/18 into 154.8 into 5/18, and the whole SI unit of this kinetic energy will be what? It will be joule. It's a little bit difficult calculation. If you are not able to solve it, what I suggest you is, instead of writing like this, instead of multiplying with 5/18, you can simply 154.8 into, how do we convert kilometer into meters? We multiply it by 1000. And how do we convert hours into seconds? We divide it by 36, multiply it by 3600. Right? This cancels out, and again when we reach at the same point, but this is the square, don't forget, and try to solve it like this as well. Done? Okay, answer in the comment section, everyone. I will see. Done? Answer in the comment section. Great. Next beta, let's move on to our next topic, that is our potential energy. Now we studied that mechanical energy was of two types, that is due to the motion of the object, due to the position of the object. Now how do I make you understand the position of the object? How many of you have played archery, right? And when you pull the arrow below, when you pull that string, this is the arrow, okay? How will I do that? Whatever. So when I pull this arrow behind, there is a string here. There is a string here. It's rubbery, it's elastic. So when I pulled it down, and now I'm doing what? I am giving this arrow a lots of energy. Now it has so much capacity to go and do the work. So because of this string, because I pulled it, it stored energy in it. And when I leave it, it will go. Done? Until the arrow is not moving. Until arrow is behind. Until arrow is behind, it is storing some energy. It is at rest. And at that point, before you leave the ribbon, before you leave the string, before you leave the arrow, until that point, it is at rest, and at the time of rest, it has some energy in it. Of course, it has some energy in it. That's why it goes, right? So that energy is in the form of potential energy. So the energy stored, that energy was stored inside the arrow, right? So the energy is stored due to the deformation, right? Deformation of that string, the energy was stored, or relative position. What do I mean by relative position? See, when we placed a pot on the top of a hill or our building, so what happened? It had some energy in it due to the height it had. Why? Because when I take away the building from that pot, it comes down, it crashes. It crashes due to that stored energy in it, because of its position, because of its height from the ground, and that is why this energy is called the stored energy. We don't see it. It is not moving. It is at rest, but it is stored inside. It is stored inside. That is called potential energy. Just like you have the potential to win this world, you have the potential to score good marks in your classes. You just have to go and do the work with the capacity, with the potential you have in yourself. And that is how Aditi Ma'am does the great talks. Okay, now this is beta potential energy, right? Just like that, we have springs, right? You have driven some bikes with good springs, or I've seen that hydraulic, let's just leave that out. Let's say you have some spring and you have attached those springs under your feet, right? Now you press it on and you get to jump, and the jump is higher than you will jump before the springs, without the springs, right? So what is happening? These springs, when they contract, these springs, when are they contracted, they are storing so much energy in these, and when you leave it, they'll give out so much energy, and they will relax now, and they will impart that energy to you, and you will jump high, just like on trampolines, right? So these are the basic examples of energy stored inside the objects, and the stored energy due to the deformation. Spring also got deformed. We pressed it, we contracted it. So it stored energy due to the deformation. Pot was placed at the higher height of the building, right? So it had a potential energy due to the height. Okay, ma'am, you are talking about potential energy due to the height, due to the height, due to the height. What is this? Beta, potential energy due to a position depends on the height it has, mathematically mostly. Okay, of course the arrow we suspended also had a potential energy, but mostly when we talk about mathematically, we include height when we talk about potential energy. Okay, now beta, this potential energy, yes, basically, okay, I'll come to that. Now we talked about arrows, we talked about springs, we talked about magnets. I told you I told you about charges, right? Let's change them with magnets. I have two magnets. Both of the north poles are toward each other, right? Now what they will do, have you played with magnets? You try to bring them closer, but the poles are similar, right? So they will they will repel each other, but you are trying to bring them closer. So you are imparting energy, you are giving them energy, but they have some potential. As soon as they are so slightly here, as soon as you leave them, you'll see they'll repel each other. Why? Because due to that repulsion, they had some energy in them, but you didn't let them move. So they were at rest. Because of that stored energy, when you left, they repelled each other and went away from each other. Now, when we talk about height, the main thing is that height gives us gravitational potential energy. What is that? Gravity. Isaac Newton sir. Everywhere you see here and there, you will see Isaac Newton sir. Okay, so pranam them. Okay, now after the pranam, we'll move on to the topic, that is gravitational potential energy. Beta, if I jump, I'll come down. I don't go up, I don't fly away. Okay, even a very patla person or a thin person will try to jump and still won't fly away, right? Why? Because the gravity is pulling us down. Gravity is constantly pulling us down. I suppose I stand on a chair. Okay, now because of this chair, I have this barrier and gravity is still pulling me down, but chair is in between me and gravity, and it's telling, I won't let Aditi Ma'am, I won't let gravity to pull Aditi Ma'am down. It was like, okay, and when I jump, I come down because of what? Very common sense. Because of what? Gravity, right? That means, beta, but when I'm on the ground, when I'm like literally on earth, I'm not getting pulled inside the earth, right? I'm not getting pulled inside the earth. So what glitch is this? What is this glitch? So now obviously I am still getting pulled inside, not inside the earth, but that land is the barrier, let's say. But what I'm trying to say, beta, whenever you jump, you attain some height. Whenever you stand on a chair, you attain some height. Whenever you stand on a desk, have you stand on desks in your school? From that I remember like the movie Dead Poet Societies. Have you seen it? Whoever has seen it knows the scene I'm talking about, Oh Captain, My Captain. That was kind of one of the movies that inspired me to become a teacher. So I hope I can be Oh Captain, My Captain someday to someone. If you have seen that, comment down, Oh Captain, My Captain. Okay? Okay, Captain Aditi. Now, Captain Aditi is standing on a chair or a desk, and I'm saying, Oh Captain, my Captain, and then I'm jump out and I go down, right? So now I'm doing what? I am attaining some height. On a chair, I have some height. When I jump, I have some height. So that height, beta, this is the ground. Okay, let me specifically point out that this is the ground. When I attain some height, edge, now I am here and I am laughing around, but gravity is pulling me down. So this gravity will pull me down, and we saw in the forces that what is the force with which this gravity will pull me down? That force, ma'am, is my mass into acceleration due to gravity. Acceleration due to gravity, right? Now let's find out the work done here. This work done on me is done by what? It gives the capacity, this energy. This is what? It is potential energy. But potential energy is what? It is the capacity to do the work, my capacity to go back to the ground, right? So that is work done, right? But is also equal to potential energy. Now this potential energy, beta, work done is what? Force into displacement, force into displacement. Now force is what? Mg, by which I am getting pulled down. That is this force mg, right? So m into g. What is the height I am traveling? I am at the height of h. When will I stop? When the height will be at 0, that is my ground, right? So this final height is what? It is h, right? So the displacement I will be covering is what? H. So the displacement is h. So this, beta, is your very important formula of this. What is this? Okay, what is happening? Okay, so whatever. This is the formula of your potential energy. Why? This is the formula specifically for gravitational potential energy, because when we attain a height, we have some energy stored in them and gravity is pulling us down, so that energy stored is potential energy due to the height, and the formula is simply, the formula beta is simply mgh. Understood? The formula is simply mgh. Good? Great. I hope you understand it really good. So this object, it is at the height of h. So what will be its potential energy? mgh, right? And h is simply h. So that is fine. But now tell me one thing. This is a block. This is placed on the ground. So what will be its height? Ma'am, its height will be simply 0. So what will be its potential energy? mgh. Potential energy will be simply mgh. Ma'am, h is 0. So what will be this? mg into 0. Hey ma'am, really? So beta, whenever we talk about potential energies, we talk about they are on a height. Gravitational potential energy on a height, right? So whenever the object is on the ground, the height becomes 0. The height becomes 0 and the potential energy will also become 0 on the ground. Understood? On the ground. Great. So whenever we are at a height, potential energy will be mgh. Whenever you are on the ground, height is 0, potential energy will be 0. Done? Understood? Great. Okay, that was the hard part actually. Now coming to a very important topic, and the topic we talked about, beta, conservation of energy. Right? I told you that energy can neither be created nor be destroyed, but can be converted from one form to another. Now we have to apply that law to our mechanical energy. Mechanical energy was what? Due to the energy due to the motion or position. Due to the motion, it was kinetic energy. Due to the position, it was potential energy. Right? And we mainly studied about gravitational potential energy. Right? Now beta, this mechanical energy is basically the addition of kinetic energy and potential energy in all the cases. Now what are you saying? You said these are the types of mechanical energy. Now you are saying these are the addition of mechanical energy. Yes, these are the types of mechanical energy, but actually mechanical energy is the addition of kinetic energy plus potential energy. Let's see how this works. Now beta, when I talk about conservation, what I mean is that mechanical energy, okay, is always equal to my kinetic energy plus potential energy. Now, what do I mean when I say that this is conserved? That means whenever, see, mechanical energy equals to kinetic energy plus potential energy. Now, let's say final mechanical energy is 10 joules. Okay, but kinetic energy and potential energy, so that means kinetic energy plus potential energy should be equal to 10 joules simply. But they don't tell you that it should be 5 or 5. It can be equals to 5 joule plus 5 joule. It can be equals to 1 joule plus 9 joule. It can be equals to 9 joule plus 1 joule. It can be equals to 7 joule plus 3 joule. You understand the point? And all these are equals to 10 joule, are equals to 10 joule, are equals to 10 joule. So when I say conservation of mechanical energy, I mean the total mechanical energy, not the alone kinetic energy, not the alone potential energy. When you add kinetic energy and potential energy, both of these collectively should be conserved. This mechanical energy should always be conserved. Okay, and let's see a very important example of that. Now how will you write it? See beta, most of the times you will write potential energy as U. Okay, U will give it the symbol U. For higher classes you will understand why. but the basic of it is kinetic energy plus potential energy. Great. Okay, now this mechanical energy is equal to K plus U. Understood? Now let us see a very important example that will definitely come in your examinations and you will have to be prepared for that. Okay, now yeah, here. Now beta, let's say we are standing. Now one more thing I have to tell you before this is the concept of relative position. We've studied about a word called relative position, right? When I say that my pot is at a height of 100 meters from the ground, right? So that means this is the ground and this is the building and it is at 100 meters and my pot is at the top of the building with very good flowers blossoming out of it, right? But I have a house near this building, okay? I have this very beautiful house near this building, okay? Now beta, this height of this house is 20 meters. Height of this house is 20 meters. So I will say that the pot is at a height of 80 meters from me. 80 meters from me. You're getting my point. So if I'm standing at here on the roof of my house, I will say, oh, the pot is at 80 meters height. But a person standing here is like, hey, are you mad? The pot is at a height of 100 meters and we'll fight and nobody will win, because I am using a concept of relative position. He is using a concept of position. Why? Because he is measuring from a point called ground. I am measuring from a point called any point, let's say A point, okay? So from A, this to this pot, this is relative position with me. Relative position with me means at what height this pot is with respect to me. At what height this pot is with respect to this person. So it is relative, it is different for me and him. Both are correct, right? So I will write the height of this pot as 80 meter with respect to Aditi Ma'am, right? I will write it like this, but this person will write that height of pot is 100 meters with respect to the ground. Both of these are correct. If you don't write these things with respect to, then this is wrong. But if you specify with respect to what, then it will be correct. Okay? Both of these are correct. Now, you will understand why I told you this concept. Okay? Now, beta, let's say this is ground. Okay? This is ground. There is an object here. Okay? Then you throw this object or whatever. This object attains a final height. Okay? This object attains a height, and this height from the ground, beta, it is h. Okay, but at some point, if you leave this object in the air, it will come down, right? It will start to come down, right? And let's say at some point, this point, we again checked it. Okay, now is what is the height? We'll say the height is h dash. Okay, h dash. Done. So, or you call it h prime. Okay, I like to call it h prime. Okay, so we'll call it h prime. So the height, when it attained its maximum height, that is h. At some point we saw it, okay, where the box is, when will it reach the ground. So now the height is h prime. Okay, and at this point the height will be what, beta? It is at ground, height is 0. Right? So these are the three cases. The case A, the case B, and case C. Done? Understood? Okay, great. Now beta, you tell me, you have studied this, right? We've studied in the motion chapter, right? That when we throw something out, it will up. When we throw something up, it will attain a maximum height, and at that height, just before it starts to come down, it will come down under the influence of gravity. Just before it starts to come down, its velocity becomes 0. Its velocity becomes 0. So at this point, can I say that we are going to watch it fall down? Okay, so this is its initial velocity. I am here, I am standing here, I am looking that the object has attained its maximum height. Okay, now it has attained its maximum height, it starts to going down, but at this instant, very second, its velocity is 0. okay, and then it attained some velocity v and it is coming down with the velocity v with the acceleration g. Okay, let's not write this v, we'll write it is coming down with the velocity of g with the acceleration due to gravity, that is g, right? And let's say at this point it had some velocity v, and again when it reaches this point it has some velocity v final. We'll rectify when we do the calculation. Okay, now let's study the point A first. Let us study the point A first. Now beta, what is happening? I am doing conservation of mechanical energy. Let me write it very clear. Mechanical energy is what? Beta, it is kinetic energy plus it is potential energy. It is kinetic energy plus it is potential energy. Understood? Now, I know the formula of kinetic energy is half mv square. The potential energy is mgh, and this is my total mechanical energy. Now I have to prove that at each of these points, what are we proving? What are we trying to do? We are trying to do that even at height h, even at height h prime, even at height 0, my mechanical energy, not the kinetic, not the potential, my mechanical energy remains conserved. It remains constant. How will we do that? That's a task. Okay. Now beta, let's understand this very carefully. I will write a little shorter, okay, so that we complete everything on this single page. Okay. Just give a second. Okay, great. Now beta, let's understand this very carefully. What is happening? Case first at the position A. Okay, what is the kinetic energy? Ma'am, kinetic energy is simply half mv square. Okay, so that means at point A, at point A velocity is 0. At point A velocity is 0. So I will have half m into 0 square, right? So kinetic energy will be 0 at point A. At point A. Yes, at point A, kinetic energy is 0. Done. Next beta, talking about potential energy. When potential energy is what? Potential energy is simply mgh, right? So mass of the ball is whatever, g is simply acceleration due to gravity, and h is what? Ma'am, at point A, h is h. So, potential energy comes out to be simply mgh. Now, what is the mechanical energy? Mechanical energy is equal to kinetic energy plus potential energy. Understood? Kinetic energy is 0. Potential energy is mgh. So, final mechanical energy will be mgh. Understood? Final mechanical energy is mgh. Got it? Done? That's the point A. Calculation of point A. Done. Now, let's see the point B. Let's see the point B. Done. Point B will be beta, at point B, kinetic energy will be what? Okay, this calculation is a little bit bigger, I'll say. Okay, so I will do this. Now, kinetic energy is the what? Half mv square. Done. Okay, ma'am. But what is this V? What is V? How do we calculate V? See, now we have learned equations of motion. Using third equation of motion, V square equals to U square plus 2AS. Okay, now this object is coming from here to here. So this is initial point, this is final point. Initial velocity is what? Initial velocity is 0. So this is 0 square plus 2G is acceleration due to gravity. S is what? S is, ma'am, this point, this is the total displacement this object covered when it fell from A to B, right? So, A to B, what is the distance? Ma'am, this whole is h, this is h prime. So, this will be what? H minus h prime. This will be h minus h prime. Understood? So, beta, what will be this S will be? This S will be h minus h prime. Understood? This h will be h minus h prime. Got it? Okay, can I have to do it the whole manually because this whole is not working. Okay, done. So this H beta is the displacement will be H minus H prime. Why am I doing this? Okay, so that you can see clearly. Done. Okay, now beta, this is equal to V square. Done. So can I put this V square here? Right, directly V square is what? V square comes out to be, this 0 cancels out, 2G H minus H prime. This is your V square. Done. This is your V square that we want to put it in the kinetic energy. So kinetic energy comes out to be what? Half M, this is V square, not just V. So directly put it here, 2G H minus H prime. Understood? Now this 2 and 2 cancels out. So kinetic energy comes out to be what? M G H minus H prime. Okay? This is my kinetic energy. Now, mechanical energy is kinetic energy plus potential energy, right? So, let's calculate potential energy as well. What is potential energy? Simply mgh. What is the height? Till here, this height you will not see this one. The potential energy is the height always from the ground up. Okay? So, at this point B, what is the potential energy? H prime, mgh prime. So that will be mgh prime. Okay, so that is your potential energy. Now, ma'am, what is the mechanical energy? Mechanical energy is kinetic energy plus potential energy. Now look at the calculation very clearly. Okay. Kinetic energy beta is what? mgh. Can I write it? Can I multiply it inside mgh minus mgh prime plus potential energy is what? mgh prime. Now this mgh prime minus this plus cancels out. So mechanical energy left is what? Mechanical energy left beta is mgh, which is exactly similar to your first case, that is at point A, mgh. Understood? The final mechanical energy in the first case at point A is also mgh. At point B, it is also mgh. Now what will this be at point A? How will I? Okay, let me make some space. Oh, I am not able to. Okay, whatever. Why am I not able to move this? Okay, I'll just delete this. Now, beta, let's talk about the final case that is at ground, that is your C. Okay, so just understand this. Okay, now beta, let's see the last, that is your at ground. Okay, at ground, H is, I will just delete this. Okay, yaar. Delete and delete. So basically at ground height is 0. Now see this, at this ground kinetic energy is what? Ma'am, half mv square. Right? Now again this v square will be found out by this same formula, but now something is different. What is different? Ma'am, similarly we'll say v square minus u square equals to 2as, but in this case u square is 0, but 2a is still g, but displacement is what? Displacement is h. Displacement is h. From A point to C point, displacement is h, right? So this will be 2gh. So v square beta will be what? 2gh, right? This is 2gh. Now I'll put this 2gh here. Kinetic energy comes out to be what? Half m into 2gh. 2 cancels out. Kinetic energy comes out to be mgh. Done? What is potential energy? Potential energy, ma'am, is actually mgh, but at this point height is 0. So potential energy is simply 0, right? So what will be the mechanical energy? Mechanical energy will be kinetic energy plus potential energy. That will be mgh plus 0. So mechanical energy comes out to be mgh. Again, the exact same in the first two cases. Exact same in the first two cases. So at B, at A, at C, mechanical energy is mgh, mechanical energy is mgh, mechanical energy is mgh, and hence proved that in all cases mechanical energy is always conserved. And yes, they can ask this derivation. That's why I gave so much time on this particular topic, because it is important. This diagram is important, this A part is important, B part is important, how you calculate this final velocity, that is important, this kinetic energy, everything is very, very important. Okay, everything is very, very, very important. Make sure to revise this, write down this again and again if you want to score good marks in your exams. Done? Okay, very good. Let's move on to the next question we have for you, and after that we'll move on to some simple machines, some more numerical, some more questions. Okay, now what will be the magnitude of velocity of the child on reaching the bottom of the slide of height h? Actually, you already did a part of it, but let's do it again. Okay, let's say beta, this is the slide. This is the slide, right? You have ridden the slides. Okay, of course, you have all probably gone to park, or you're just scrolling reels all day from the starting. I hope you went to parks. Okay. Okay, we want to find the magnitude of velocity of the child. Okay, a child is sitting here and he's coming down. Okay, on reaching the bottom of the slide, this is the bottom of the slide, right? Now the height of the slide beta is simply h. Okay, and here the height will be what? Height will be 0, right? Now we will do using conservation of mechanical energy. How will we do that, ma'am? See, this, I know that in this whole thing we learned that mechanical energy here is equal to mechanical energy here is equal to mechanical energy here, or everywhere in between, right? So mechanical energy at point A will be equal to mechanical energy at point B as well, that is on ground. A is on height h. So the basic, using by, how will you write it? By using conservation of mechanical energy, or basically we write it as law of conservation of mechanical energy or energy, but you can simply say conservation of mechanical energy. We write it beta as mechanical energy at point A is equal to mechanical energy at point B. Understood? At point A, it is kinetic energy at point A plus potential energy at point B. Potential energy at point A equals to kinetic energy at point B plus kinetic energy, plus potential energy at point B. Kinetic plus potential at A, kinetic plus potential at B. A, B. Done. Now beta, let's fill out the formulas. What is the formula of kinetic energy? Half mv, let's write A square, plus mgh, height at point A, right, equals to half mv square at point B plus mgh at point B. Understood? This is clear? Now beta, what is the v square at A? What is the v square at A? Beta, final, it is at rest. It is at the highest point. A child will be at rest at the start of the slide, right? So this VA is 0. This VA is 0. Half m 0 square. Okay. What will be the... Okay, they have not given, but you will take V of A as 0, right? So here the velocity is 0. Okay. Here we have velocity as V of B, right? Here the height is h, height is 0. Okay. Now height is what? Mg. H of height A At point A, height is what? H, simply H, right? Now, half m VB square is actually we have to find, right? Of course, now you'll say, ma'am, kid also stops at the bottom of the slide. Actually, it doesn't, right? It slides into the mud. So when that slide is ending, there's a red color slide, that slide is ending, he doesn't stop. He slides out there from that slide, he slides out, right? So that is the main thing. Now, half m VB square is at the end of that slide, okay? Plus MGHB, MGHB, ma'am, HB is 0, okay? H is 0, right? So what is 0 now? This is whole 0 plus MGH equals to 2mVB square plus 0. This is the final equation at this particular instance of our calculation. Okay, let's move ahead. So what we have? 0, we have 0 plus MGH equals to MVB square, half of it, plus 0, right? That is the case. Now beta, see carefully, this 0 has no value, so simply it goes MGH equals to half m VB square. This m and this m cancels out, right? So this 2 goes and multiplies there. 2GH equals to VB square. If we take the square root on both sides, then the square root and the square gets cancelled. We have VB equals to under root 2GH. Do you know how important this formula is? Have you heard of BARC, ISRO? Even they ask this formula. Even they ask this formula. So beta, what does this mean? That at the end of the slide, the velocity of that child is completely dependent on the height of the slide and acceleration due to gravity. That is also 10. That is always 10. It is always 10 or 9.8. Whatever we take, but that is constant. Height changes, so that means higher the slide, higher the velocity, lower the slide, lower the velocity. Okay, so ma'am, that means if a very thin guy, if a very light guy take the slide, he will have same velocity at the end of the slide, and if a very motu bacha, very motu person takes that slide, he will also have the same velocity. The mass of the child does not matter, as it shouldn't in any case, but slide is not fat phobic. Why am I talking she? Okay, this slide is not take into account the mass of the child. It gives equal velocity to all the people who takes that slide, and we should learn something from it. And beta, this is a very, very, very important point. Okay, at the end, see, if you have missed this here, see, this also come v square equals to 2gh. That means this is just about a slide. If I take a ball, if I throw it up, it will reach a maximum point. Here the u will be 0. It will come down at some place, at downward the velocity will be v. Now try to find the displacement or the velocity, final velocity. This is h. This is h. What will be this? V square minus u square equals to 2as. That is your third equation of motion. V square is simply v square. U is what? 0 equals to 2. It is coming down with acceleration g and displacement is h. So v will be again 2gh. So does not matter even if it is you are coming down slanted, you are falling down. In every single case, when you hit the ground, your velocity will be under root 2gh. It does not matter on the angle, it does not matter on the mass, it does not matter on anything, just the height from which a person or a thing is dropping. Only that decides the potential energy, only that decides the velocity at the ground, velocity at the bottom. Done? Very important point. Okay. Okay, great. Now let's move on to some very starting of simple machines. This is actually not a simple machine but a pendulum. Okay, what is a pendulum? Better, this is a very easy concept, very good concept. You just have to learn some technical terms, that's it. Other than that, it's just common sense. This is your pendulum. When you take this pendulum here, you have seen a swing, right? A swing in the park, right? So you sit on it, you go behind, and when you are coming back, you go there. That's the highest point you can go. When you come there, does the swing stop here? No, it goes in the opposite direction, right? And when you go there, again it comes back, it goes in the opposite direction. And this is how you are swinging now, right? This is what? This is a simple pendulum. You take a thread. I'll give you homework. Take a thread, tie some heavy ball and try to do this. Not the whole ulta pulti, but just take it this and leave it. You will see that it's not stopping here. Basic common sense. It will go in the opposite direction. But we have to see the energies at this highest point, at lowest point, at highest point. That's our work actually. Okay. So what happens, beta? This is the pendulum, okay? When it goes to this extreme position, this is called extreme position. Yes, scientifically, this is called extreme position, the highest position. Its potential, it has only potential energy. Why, ma'am? When you go to top, velocity becomes what? It becomes zero. Right? When it goes there and just before coming down, its velocity has to become zero, right? Then only it will come down. So velocity is zero. Velocity is zero. Kinetic energy is what? Half mv square. If velocity is zero, kinetic energy is zero. It only has potential energy. Now, beta, now see, now we are talking about relative positions. This is the position we are taking our distances from. No matter where the ground is, this is where I'm measuring. When I'm measuring that, this is the height of extreme position. Let's say this is ground. Okay, but I am not measuring from ground. I am measuring from this position, the last position of this pendulum, the length of this pendulum, the lowest point of this pendulum. That is from where I am measuring the distances. So till here, this height of this, when it goes to extreme position, it's let's say h. So its potential energy becomes mgh. However, ground is even h prime below this h, right? But we are not taking that, okay? We are doing the relative position concept. So at this point, my height is 0. I am taking my height as 0. I am measuring it from at this point. And the pendulum is going like this. It is touching this point, okay? So this is my 0 height. So here, beta, if height is 0, mgh, h is 0, h is, so potential energy, mgh, h is 0, potential energy will be 0. It only have kinetic energy at this lowest point. Okay, then again it goes to extreme position on the other side, and now again here its height is what? H. So its potential energy is mgh, but kinetic energy is what? At the highest point it will be 0, because why? V is 0, V is 0, so kinetic energy beta will be 0 and it will only have potential energy. So what you have to remember? At the extreme position, the height will be h, the v will be 0, and hence only potential energy will be there on the left hand side, on the right hand side. The potential energy will be there, but the kinetic energy will be 0. At the lowest point, that is your mean position. What do you call it? Mean position. At mean position, beta, you will only have, your pendulum will only have kinetic energy. Why? Because h is 0, mgh is potential energy is 0. Then, and we of course know it has some velocity, that's why it goes into another direction, so it only has kinetic energy. Okay, the bob released at P rises to nearly the same height at R. Mechanical energy is conserved. Mechanical energy will be conserved only if this height is equal, right? This is mgh. If height is 10, this is mgh, height is 9. How will potential energy be conserved? But in actual practice, this doesn't happen. Why? This is an ideal case. Why? That means air resistance is not there, gravity is not there. We are doing it in vacuum. So there is no loss of energy, no friction, no air resistance. But when I do it here, there will be air resistance, right? When you come down, you feel lots of air on your face, right? When you come down on a swing, and you will see that your swing is getting slower and slower, right? Actually, in higher physics, you will learn about this. These are damped oscillations, damping. Okay, so we'll study about this, but right now you just study that this is an ideal case. So this height at P point and height at R point is same. That's why potential energy is same. Okay, that's why mechanical energy is conserved. Okay. In real life, friction at the support and air resistance slowly steal energy and it stops, just like I told you. Done? Okay, moving on beta, we have a very important, okay, we did this, right? Potential energy at the top, kinetic energy at the bottom equals to mgh equals to half mv square. So v equals to root 2gh. How did they do it actually? They did it with the help of mechanical energy, conservation of mechanical energy. We did it with the help of simple equation of motion. How did they do it? Beta, at the top v is 0. So kinetic energy will be 0. Potential energy will be simply mgh. Right? At the lower end, kinetic energy will be half mv square. Potential energy will be mgh, where h is 0. So potential energy is 0. Now at this point we only have potential energy. At this point we only have kinetic energy. Now according to our law, both of these points should have same mechanical energy. That means at this point mgh, mechanical energy, should be equal to plus 0 kinetic energy should be equal to 0 potential energy plus kinetic energy half mv square. This 0 0 goes. So mgh equals to half mv square, just like we did it in the case of slanting, right? So that's the same. Mm cancels out, v becomes root 2gh. So these are the two ways, using equation of motion and using the potential this kinetic energy, you can calculate the velocity at the lower end of a slide or anything, right? Okay, great. Next beta, we have one more fun fact, that is the unit horsepower exists because James Watt compared his steam engine to real horses. So 1 horsepower is equal to 746 watts. 746 watts, do you understand? 746 watts of power is in just one single horse. But ma'am, what is power? That's a real question. So let's study about power. Now beta, power is simply the power inside you. Okay, now let's say I will take an example that you and your friend, you bet, and your class is at 3rd floor. Okay, and you both go there. Now at the 3rd floor, let's say the height of this 3rd floor is simply 30 meters. So at the end, you will be at rest when you reach the 3rd floor, right? You're sitting. Your mechanical energy will be simply potential energy, and that will be mgh, and it will be, and let's say you have same mass, so it will be same, right? mg into 30, right? So your potential energy is same, right? But you are more powerful than him. Then how do you have same energies? That's a task, ma'am. That's a confusion. Now the concept becomes power. Power beta is not just energy. Power is not just work done. You reached the 3rd floor in just 2 minutes. He reached the 3rd floor in 3 minutes. So of course you are powerful. You have more stamina. You have more power in you, right? So actually power is the rate of doing that work. Rate of doing that work. We have studied about rate of doing work, right? Whenever you see a word rate, that means you divide that quantity with time. That means beta, you have the capacity to do the work, you are doing the work. So it takes you 10 joules to reach that 3rd floor, but you did it in 2 minutes, and your friend also has to work 10 joules, but he did it in 3 minutes. So your power is different. Your power is 5. Okay, let's say just say 5, and his power is 3.333 only. So your power is more than him, right? So what is power beta? Work done, the work you did per unit time. Per unit time. Running upstairs in 1 minute versus walking up in 5 minutes. It is different. Same work we are doing, but different power. So power is what? Rate of doing work. Rate of doing work means work done divided by time. work done divide by time. Understood? Work done divide by time. Okay. Now what is the SI unit, beta? The SI unit of power is simply watt. SI unit of power is simply watt. Okay, and we say watt laga rakhi hai, so this power I actually say I have a very good phrase, that is hum watt laga denge physics ki. Why? Because we have the power to entertain this mess of physics. Okay, we have watt laga denge physics ki. Done? Okay, so beta, this you can also remember that 1 horsepower is equal to 746 watts. Okay, and it is named after James Watt. What is the formula of power? Ma'am, work done upon time. This is the main formula of power. Okay, main formula of power. Okay, great. Now beta, let's do a very important numerical. A weightlifter lifts a 75 kg mass. Okay, so mass is given as 75 kg in 2 minutes. Okay, by 2 meter. Okay, distance is given as 2 meters in 5 seconds. Time is given as 5 seconds. Okay, lots of things is given. How much power would she require for this task? So this beta is given. We have to calculate the power required to do this task. Now ma'am, power formula is simple. We know the formula of power is work done per unit time. Work done per unit time. Now she is lifting it, right? She is lifting this particular weights, right? She is lifting the weight. So when we lift something, which energy do we get? We get potential energy. Correct. So this is simply what? mgh per unit time. M is given, that is what? 75 kg. 75 kg. G I will take as 10 here. What is the height? Till what height did she manage to lift it? 2 meters. Right? 2 meters, and everything is in SI unit. That's you have to make sure. Kg, SI second, SI meter, SI. Great. Okay. Then beta, the time is what? 5 seconds. So you will just multiply this. This will be what? 275 into 4. That will be what? 0 and 300 watt. Correct? That is our final answer. She will require a power of 300 watt to lift a weight of 75 kg to a height of 2 meter in 5 seconds. Understood what I told? Okay. Okay, beta. The second portion of this chapter is finally complete, and we are moving on to the last section. That is our simple machines. What is that? Simple machines. Great. Now beta, simple machines is basically one thing we have to look for simple machines. That is our mechanical advantage. But what is simple machines before we go into that? Now, you threw some box and your mother is like, take it out, and it is like 10 floors down from your building, right? So you throw a wire and somehow it's a magnet and you have so much brain, it gets stuck with that wire, with that rope, and you're pulling it like this. It is hard. That box is, let's say, 5 kg. Will this be hard, right? You're pulling it with the rope. It is hard. What if I give you a pulley here? What is that? What if I give you a pulley here and now you pull it like this? Instead of pulling like this, you are pulling it like this, the rope, and it is going through a pulley. You know what a pulley is, right? So you're going through a pulley and the weight is coming down. Which one will be easier? What do you think? Will one be easier or one be hard? Actually, the pulley one will be easier. But there is a twist. Now, first learn about this. Okay. So basically, beta, devices that makes tasks easier. Okay. By changing the magnitude or direction. We were pulling it. We changed the direction. right? By changing the magnitude or direction of the force applied. Those are beta simple machines, which makes our work easier, which makes our work easy. Now one thing to take care of, they do not reduce the total work. If you are doing a work like this of 100 joules, like this also you will be doing 100 joules, but your effort will be decreased. Your effort, the work done by your muscles will be less, but the work done, that work done one now will be done by what? That machine, right? That's why it is easier, it is simple, right? Machines, they don't create energy, they just take a load on off from us, okay? So beta, we apply the effort, that is the force we apply. We are applying some effort, that is the force we are applying, right? The load that we are carrying is force to be overcome. The load we are carrying, that is downwards, that we need to overcome. If it's a 5 kg box and the force will be what? 5 kg into g, mg downwards, right? We have to overcome that, then only we'll be able to pull it up, right? So we'll study all about that, don't worry. One thing you have to study is that beta, one thing is called mechanical advantage in simple machines, that is load divided by effort. That means the load, that box you are carrying, right, divide by our effort. Now simple machines do what? This is the mechanical advantage. Simple machine does what? They decrease this effort, and that's how mechanical advantage increases. And by the word mechanical advantage, you can see that it is easy for us, simple for us to bear that load. Okay, now there are 3 simple machines. First is your pulley, then inclined plane, then lever. Let's study them one by one quickly. Okay, we have been here for 2 hours. Okay, first beta is your pulley. Now this is the load, right, and this is a circle. Okay, so it can rotate, like this, right? You all know what pulley is, right? Just search it up, or I think you all know what pulley is. Okay, so I am standing here, I am pulling this rope down, and this load will go up, right? This is a very important topic of JEE Mains, JEE Advanced even. So it is better if you know the basics, right? That's why NCERT included it in class, in your class 9th, right? So we are making an effort in the downward direction. This load is coming in the upward direction, right? Earlier when this pulley was not there, what do we have to do? We have to apply the force also in the upward direction and displacement in the upward direction. But now we personally are applying the effort, the force in the downward direction, and because of this pulley, this load is going up, right? And hence that is why pulley helps us. It makes our load, it makes us work less. Okay, so beta, a wheel with a groove that guides a rope. There is a wheel, right, a round circle kind of wheel, and you put a rope across it, and when you pull it, it will move with it and make our work simple, right, to lift up the loads. Now fixed pulley, what is that? It doesn't reduce force, only changes its direction. That means beta, it did not reduce the force we are applying on it. We were applying the force like this, but now we are applying the force in the downward direction, so it changed the direction of the force. You must have seen these in many construction sites as well. So why they use it? Because it decreases or changes the direction of force. Work is same, but now the work is done by, a little bit work is done by machine, but the force is same, force applied is same. Okay, then beta, see, this is the main part. Pulling down is easier than lifting up, of course, right? Pulling down is easier than lifting up. That means beta, our mechanical advantage will be equal to 1 only. Done? Mechanical advantage was what? Load divided by effort. So we are applying the effort. Load is coming up. So mechanical advantage is equal to 1. Done? But beta, a movable pulley, that is pulley systems, mechanical advantage is greater than 1. Mechanical advantage is greater than 1 means what? The load is heavy, effort is less. Load is heavy, effort is less. If this is load is 2, effort is only 1, so mechanical advantage is equal to 2, so mechanical advantage is greater than 1, right? So it is good, right? Advantage, mechanical advantage is greater than 1, and that is the main part. Beta, mechanical advantage, when it's greater than 1, we can lift heavy loads with small effort. We can lift heavy loads with small effort. Like what? Like our lifts used in cranes, elevators, lifts, right? So that what makes this pulley a very advantaged machine. Okay, done, understood? For heavy loads, mechanical advantage of the pulley should be greater than 1. Okay, done? Very good. Now beta, let's move on to the second, that is your inclined plane. Now beta, you tell me one thing. Have you been to mountains? You've been to mountains, right? And when hairpins come, they are very steep. Will it take us more work to go there? And normal hair, not even a hairpin, normal inclined plane. Will it take us more energy there, work there? Of course, ma'am. Of course, in the more inclined, there you are doing a trek, and it's very steep. It will be hard to climb that, rather than a trek that is not that steep, that is on the other hand simple, right? Comparingly simple, right? So beta, moving up a ramp needs less force than lifting straight up. What does this mean? That you have to lift something and put it in the truck. There is a truck, you are moving houses, and you have so many big beds. So what will they do? They will place an inclined there, right? An inclined plane there in the truck and the ground, and you will go up, right? You will go up from that inclined plane. Then it will be easy, okay, rather than lifting that bed up and putting it in the truck. Done. That is one thing. Okay, so that's why they say moving up a ramp is like this, right? Needs less force than lifting straight up. So whenever you want to lift something hard, make sure you build a ramp like this and push it up rather than lifting it and keeping it there. Okay, so work stays the same. Work stays the same, and this all thing happens over a longer distance. What do we mean by that? If I want to go here till here, and if I want to go at the same height but till here, so this ramp will have more angle, this ramp will have smaller angle, right? So climbing this is easy rather than this, of course, right? You are reaching the same point, same height, but if you travel a longer distance, it will be easy to travel. If you climb a higher inclined distance, it will be hard to travel, hard to get up, right? Understood? Now beta, one more thing, at that point your potential energy will be what? mgh. Let's say this height is what? This height is h. Okay, so this is your potential energy, and the force you are applying to go there, let's say that is f prime, right? F prime, and this length is L. Okay, this length is L, so it will be L, right? Work done is equal to potential energy, right? The capacity to do the work is the capacity to do the work. Yes, it's energy, and at that point, highest point, you are at rest, just the potential energy, that is mgh, right? So beta, this f dash h, you can write this simply as m into a into L equals to mgh, right? So if this cancels out, your g into h will be a into L. That's the one point. But if we want to keep it as f dash, what you will do? Okay, just don't use it as ma, just keep it as mg divided by L, this L goes here, equals to f dash divided by h. Okay, now this mg is what? Mg is simply force due to gravity, right? Mg is simply the force due to gravity. Okay, so you can simply say f divided by L equals to this f dash divided by h. F dash is the force that is taking you up, mg is the force that is pulling the gravity down. Okay, or you can simply just stay here as well, stay at this point as well. Okay, what is the main that? Okay, you can also write what is the, okay, that is one thing we have to remember. See, mg, if I take f dash under, f dash equals to L stays here and this h comes down, Okay, that is also one thing. Now why we did this? What is the difference between these two? Why did we these? Why did we prefer this formula over this formula? That is a very interesting case, beta. Why? Because this F dash is what? Force. Mg is also a force. This L is what? It's a length. H is also length, also displacement. So instead of this formula, we will prefer this formula. Okay, prefer this formula, and you have to learn this formula. I'll write this again. Mg divided by F dash equals to L divided by H. L divided by H. L is the length of the inclined plane. L is the length of the inclined plane, beta. Okay. H is the simple height till that highest point, right? And F dash is the force applied. It is the force applied to go up that inclined plane. And mg is the simple weight due to gravity or force due to gravity. Done? This is the formula you need to remember in case of your inclined plane. In case of your inclined plane, very, very, very important. A question will come from there, right? So based on that, let's do a question. A person uses an inclined ramp to raise an object over a step 30 centimeter high. Okay, so height is beta 30 centimeter. The ramp has a width of 40 centimeter. Okay, so this is your ramp. The height beta is 30 centimeter. The width on the other hand is 40 centimeter, right? The width on the other hand is 40 centimeter. What is the mechanical advantage of the ramp that helps the person achieve the task? What is the mechanical advantage, beta? Mechanical advantage. Now, what was the mechanical advantage in case of planes, inclined planes? That is, beta, this particular formula. What is mechanical advantage? This whole is the formula of mechanical advantage. This whole is the formula of mechanical advantage. Okay, done? Now, this is the main formula. Let's apply it in our question. Mechanical advantage is simply what? What was the formula? Mg divided by F dash, or the length of the inclined plane divided by the height. Now, do we have Mg and F dash? No, we don't. Do we have the length of the inclined plane? We don't. But we have Pythagoras theorem, right? So, of course, this is the height is perpendicular 90 degree, correct? So, can I use Pythagoras theorem? This is length, right? So L equals to square of 30 plus the square of our base, that is our 40, correct? So this will be your 900 plus 1600 equals to the length. So length will be beta 2500, but this is in what? This is in centimeters. Don't forget that. Okay, if I convert it into meters, I'll divide it by 100 and that will be 25 meters. Why did I convert it in meters? Because we want everything in SI units. Okay, let's just put the values here, and height is also given in centimeters. So I'll convert that also in meters, and that will be 0.3 meters. Done? Let's just put all these values in that formula L by H. So our mechanical advantage will be what? L by H. L was what? L was 25 meters. It was 25 meters divided by what? 0.3 meters. It was 0.3 meters. Now, you don't have to do all the calculations. You don't have to do all the calculations, but all you have to do is to see if mechanical advantage is equal to 1, or it is greater than 1, or it is less than 1. What is it there? Of course, it is greater than 1, right? So, mechanical advantage is greater than 1, and that is what we want. That is what we want, right? Height was 30 centimeters converted into 0.3 meters, correct? So, length was 25 meters, correct? And that's our final solution. Oh, okay, I realized one thing. I didn't take square here. Come on, you have to tell these mistakes in the comment section. Okay, I'm also human, bro. Okay, so L square, this is also square, so beta L will be L will not be 25 meters, it will be L equals to 2500. That will be what? That will be 50 centimeters. Okay, so L will be 0.5 meters. Still, it doesn't affect the answer. This will be 0.5, and simply it is greater than 1. So our mechanical advantage is greater than 1. That's what we wanted. Then moving on to the last machine, that is your lever. What is your simple machine? Beta, take one thing, take a scale, take a pencil and place the scale on your desk. Place the scale and pencil like this. Place on one side, place a very heavy object like a stapler. Okay, and on the other hand, place an eraser, very small eraser. And can you see, can you make this stapler go up just with the help of an eraser? If you saw seesaw, if you seated with a very motu guy, of course you will be always at the top, right? But here is a trick to win that, right? Now beta, there are 3 things in lever that you need to see. That this point where under the seesaw there is a point where that stick rod is hanging, right? That point is called beta fulcrum. Okay, there is this load and this is the effort. Now this is your scale, this is your pencil that you used as a fulcrum. Okay, next beta, this is a stapler. Okay, this is a stapler and of course it's very heavy, and you place a eraser here but still the stapler is down. So you do what? You move your pencil towards the stapler. You move your pencil towards the stapler. Now this is called load arm. Where the stapler is, from the stapler to the fulcrum to your pencil, it's load arm. From eraser to your pencil, it is your effort arm, because eraser is applying the effort, right? So if you move your pencil or this fulcrum towards the load and you place one more eraser, it is just not equal, still not equal to the mass of stapler, but you will see that stapler is coming above. It is lifting above. So small 2 erasers are lifting a very heavy stapler. Why? Because of this placement of this fulcrum, and that is the main point of lever. So whenever you are taking seesaw with a very heavy guy and he is like hanging you on the top, what you can do? You just ask the motu guy to move towards the fulcrum. Okay, if he won't move actually, but whatever, if you ask him to move, you will see that you will start to go down. And actually there is a very good concept on this, that is torque, that you will study later. Round force in the curl. Okay, I will not go into it, but it's a very good topic that will again make you come back to this, but now it will include a lot more maths and you will understand it better. Okay, so a rigid bar rotating about a fixed point. This is the rigid bar and it's a fixed point. It is rotating, or you can say lifting about the same, a small point. Small effort over a big distance. Small effort over a big distance lifts a big load over a small distance. Understand this point? Small effort eraser over a big distance lifts a big load, that is your stapler, over a small distance. This distance is from the fulcrum. Okay, and in this case beta, our mechanical advantage is what? Mechanical advantage is effort. This effort into effort arm. The distance of effort arm is equal to the load into the load arm. Okay, this is the main formula you have to learn. So mechanical advantage is what? Your effort arm divided by your load arm. Your effort arm divided by your load arm. Okay, done. In lever, in inclined plane, it was load by effort. Here it is effort arm divided by load arm. Done? Okay, so longer the effort arm, effort arm is bigger, mechanical advantage is bigger. Smaller the load arm, bigger the mechanical advantage, and that is what we need, right? That is what we need. That's why a spoon opens a can lid easily, because you are applying an effort on a large distance. This is a can, you are applying the effort here and the load is right here. So you are applying the effort at a large distance, but the the lid of the can is very near. So mechanical advantage is greater than when, and easily opens the load. Now beta, this is of 3 types. Class 1 is fulcrum in between, that is your seesaw. Okay, that is your seesaw or the scissors. Now Effort, class 2 is a load in between. We have this rigid bar, this is the load, and fulcrum is somewhere here, and this is the effort. Okay, lemon squeezer, when you see lemon squeezer, the two efforts are there, right? Lemon is in between, and at the end you have the squeezer. So you squeeze here, but the effort is out. Effort is not, the load is in between these two arms, right? Correct. So bottle opener, correct. So the bottle, the cap is in between the two openers, two ends of the openers. Then class 3, effort is in between. That is your tweezers, your broom, your hammer, or you're lifting a chapati. Okay, so your effort, you apply the effort with help of your finger. Okay, you press it. Now the effort is in between, load is there, and effort is in between. Fulcrum is at the end. Okay, from where that chimta we call it. So chimta is there. Okay, so that's the main point, beta, and that is where we end today's session. A very how will you say, traditional or patriotic feeling I get when I learn this and from this NCERT. So in Himalayas, beta, traditional water mills are built. So here is the water, okay, here is the mill, and a water comes from a hill. This is a hill, okay, water is coming. So here kinetic energy of water will be a lot, and it will make these mills move, these rotates, and these are connected to the grinder. So these grinders will move, and they will grind grain with the help of this. Okay, water at the top, potential energy, it flows down, kinetic energy, it spins the wheels, turns the grinding stone. Modern dams use the same idea to generate electricity. That's why they send water with a great flow downwards. Okay, that's the main point. Now what did we study, beta, in this whole section? Work, we started with work. Force into displacement, unit is joule, in the direction of force. Displacement is in the direction of force, or force is in the displacement of direction of displacement. Anything works. Okay, energy is the capacity to do the work. Energy, work energy theorem is delta E. Delta E means, beta, change in energy. This simply means change in energy and nothing else. Okay, kinetic energy is K equals to half mv square for motion. Potential energy, position or deformation, mgh, gravitational potential energy. Mechanical energy, K plus U, kinetic energy plus potential energy, always conserved. Power equals to work done per unit time. Unit is watt. 1 watt equals to 1 joule per second, work done upon time. Simple machines change forces, size or direction, not the work done. Remember the formulas of mechanical advantage. Okay, mechanical advantage is load by effort. For ramp, load by effort, right? For lever, it is effort arm divided by load arm. Done? Done? Okay, that is your whole chapter in a glance, in a summary. Okay, now beta, I have some few questions for you that I am giving you for homework, and you will get this PDF in the description as well. PDF in description as well. Okay, we'll do this particular numerical, and I'll give you the PDF, and you will do all other numericals by yourself. Okay, a 15,000 kg of jet. Okay, simply write what is given. 15,000 kg of a jet, an aircraft carrier, a wire pulls back with 367,500 Newton. So force is, beta, 367,500 Newton. But remember, it is pulling back, so force is negative. Okay, and stops it in 100 meters. So S, our displacement is 100 meters. What is the speed just before the landing? What is the speed just before the landing? How will you do this question? How will you solve this particular question? You tell me that in the comment section, and then I will do it quickly, fast. Okay, now beta, what happens is, this force, this work done, basically work done is what? Force into displacement, and this work done is what? Change in kinetic energy or kinetic energy, right? So this is what? Minus 367,500 into 100. What is kinetic energy? Half mv square, right? So mass is given, v we have to find. Can you do that? Mass is given, I'll write down half. Mass is given as what? 15,000 kg and v square. Now everything is given. You just equate these two. these two relations and let me know the answer in comments. Answer in comments. Although I have so many more questions in this PDF, go get this PDF in the description and your chapter is done, and these are with answers. All the questions are with answers, so make sure you get this PDF in the description. And that is it. We have completed work, energy and simple machines with a lot of effort and enthusiasm, I think. Okay, that is it for this video, beta. I'll meet you in the next one. Tada, bye bye.